where we come from, on the Great Britain, with English, you know? So we come exactly from the same city, which is called Brest. This is not a joke, the name of the city.
Yeah, the A is not in the name, actually. It's a B-R-E-S-T.
And Matthias is absolutely incredible coder. He can code crazy things, but he uses Java.
Come on, you guys, come on.
So I will let him introduce himself, but really he's going to talk to you about things that are absolutely incredible. He's working on this kind of stuff since a lot of years now.
Not counting anymore.
Not counting anymore. And just to give you an idea, I think that a couple of months ago, Facebook launched its own solution, which is exactly what Matthias do, or maybe there is some difference, but you're going to explain that?
Yeah, we'll explain that.
Okay. But one of the major differences is they use more memory and they go slower than Matthias. So that's pretty funny. So I have a very good lecture. I don't know if you call it.
Introduction to time series or whatever. Let's see if I screw that up. That's not going to work. No. Okay. So I'm going to do so. Just to make things clear, this is a conference I actually gave last week at Percona Live, which is an open source database conference. Except I took all the Percona logos off. I changed the background to gray so you could actually see it in this room. It used to be blue like that. Kind of shitty when they're so it's about time series a little bit. So I'm going to introduce that. This is not part of the slide deck I have, but I'm going to talk about it because really the world we're living in is full of time series, except you might not know it yet, right? And then I'm going to focus on what we actually build. It's a platform which is called Warp 10, which is open source. So you can just download it and install it anywhere you want and do whatever and fantastic things with it. And we'd be more than happy to know what you've built with it. So I'll deep dive into that platform to take you through some of the challenges that you will have to handle if you want to handle time series at scale. And talk about what scale means when we talk about time series. And then at the end, then you can ask me questions on whatever you want. Who made my t-shirt? What kind of cake I bring to Quam when I come over? Whatever. Why I get curly hair? Why I don't have gray hair even though I'm not that young? Okay. Why? Ah, good question. Huh? Okay, so a little bit of background on me. So I'm Matthias Roberts. I'm the CTO and co-founder of a company called Citizen Data, which makes the Warp 10 platform. I used to be a banker, not actually counting bills, but doing big data in banks. And I also worked at Google. I was a senior SRE, site reliability engineer on the big table service in Dublin. So I kind of was exposed to big data early in my life. Early being 10 years ago. I'm currently a Frenchman. That might change depending on the result of the Sunday election. We'll see. You can reach me on Twitter at Herberts. So don't hesitate to do things. Bash me if you don't like what I'm saying, whatever. I don't care, okay? So time series. So time series, I'm sure you've probably heard of time series by now. If you haven't, it's the hype term in the database world, right? There are lots and lots of time series database actually being shipped. Almost weekly, you can find a new one of someone saying, you know, all the other databases were not good enough. And I'm going to just push it out, and people are going to use it and do fantastic things with it. I listed a few on the next slide. All those are actually open source databases that are focused on time series. Some of them are logos. So the dog, for example, who asked me that? Why is that a dog on that time series database? Well, I guess the guy likes dogs. So there are some that are made specifically for monitoring, or mainly for monitoring, like InfluxDB, for example, OpenTSDB also, Prometheus, even though Prometheus, which is on the lower left, usually doesn't consider itself a time series database, but more a monitoring system. And there are some that are more wide range of problems that they tackle. Some of them are interesting. So the gorilla on the bottom right is Berengai, which is made by Facebook, which was open sourced by Facebook, I think it was in December. The second one on the top row, Timely, is made by the National Security Agency, so also interesting. So lots of different people in that space, lots of things, lots of solutions you can really choose from to handle that kind of data. But as we'll see, they usually focus on the actual data management and not on the actual value creation that you can expect from those data. So I'm going to talk to you about what I think is the best approach to actually managing and analyzing time series, of course, because we made it, right? Which is Warp 10. So today is May the 4th, be with you. So as you can see, this is a jump into hyperspace. So for the fans of Star Trek, you know that Warp 10 is actually the top speed at which the Enterprise can go, right? And for the purist among you, this is not the hyperspace jump of the Enterprise. This is the hyperspace jump of the Millennium Falcon, right? This is very important on May the 4th, right? Well, anyway, I have a few stickers here, so I don't have many left, but you're welcome to actually grab one. Please grab only one, or if you grab several, pass them to your neighbors. And also, don't try to actually scan that. This is not a QR code, right? It looks like one, but it's not. Okay, so what is Warp 10? So I'll go down into the time series detail after, but Warp 10 is a rich tool suite that was dedicated from the ground up to actually handle and analyze time series data. We had a first use case where we realized very early on that managing the data was the first challenge because time series data come at scale that you're probably not used to. And the second challenge is really making sense of that data. And when you start looking at what you need to build to actually make sense of that data, you realize that you're very far from your business objectives or from the problem you're actually wanting to solve. You have to build low-level algorithms, low-level data structures, and make sure that all that works perfectly before you can actually expect to start solving your business problem, right? So when we realized that, we thought, well, there might be a gap that we want to fill, where we can actually bring to the table a nice set of tools that people can just get their hands on and start using instead of reinventing the wheel. Because very simple things like moving averages, for example, are being written every day by people wanting to analyze time series, right? So they spend countless hours just reinventing the wheel, rebuilding some stuff, which is usually tailor-coded for their specific problem. So the next time they have to apply a moving average, they can't even reuse the code that they've written the first time because they didn't think about a generic approach to do that. So we wanted to solve that problem and actually build those tools in a generic way so people could actually use them for many different problems that they wanted to tackle. So, time series. So basically, a time series is a sequence of measurements or a sequence of values which are linked, each value is linked to a timestamp, right? So look around you, look at all the problems that you've already solved or problems that you want to solve, and you probably will find that they relate to time series, right? Logging is really a time series. It's a sequence of messages that arrive from your systems. Tracking cars is a problem of time series. Measuring temperature is a problem of time series. So those are obvious ones. Doctor appointments are a time series, right? If the interval between two appointments actually reduces and the density of appointments increases, then there's probably an outbreak of a disease somewhere because people go more to the doctor than they used to, right? If you go in a grocery store and you self-scan your products, you're also not self-scanning your products. Well, see, most people think that they are self-scanning their products, that we are producing a time series. Yeah, I know, it gets on your mind sometimes. So you're actually producing a time series of the barcodes and the various times at which you scan the barcodes, right? So the world around you, whether you like it or not, is full of time series. And at one point or another, if you actually solve problems in a smart way, you're going to need some tools that can actually handle or analyze time series. Well, we went a little bit further than simply having time series. We created a data model which is called geotime series. So basically, we took a time series and we took the location of the sensor when the various measurements were actually done, and we merged those two information together, right? So we have a data model which is those geotime series where you have sequences of values, and each value is associated with a timestamp, a latitude, a longitude, and elevation, and that gives you a geotime series, right? So that allows you to do things in an easier way than if you were actually storing different time series for the location part. Because if you're storing the latitude and the longitude as different time series, then you're going to have to do a join on the time just to actually find the location of the sensor when you measured something, and that's really not efficient, especially if you're talking millions of data points that you have to join on, or even billions of data points on thousands or hundreds of thousands of series, right? So that's the model we created. In more detail, a geotime series is really identified by two things. We have what we call a class, which is really the type of sensor that you're measuring things from. It could be temperature, it could be barcodes, etc. So you really have to think of the class as the type of things you're measuring, the type of the data that you're actually keeping track of in a sequence. Next to the class, we have a set of key values, which are called labels, which enable you to associate with the time series and define a time series by a set of key values that are meaningful for the field you're actually solving a problem in. So for example, if you're into aeronautics, you might have the aircraft registration number as a label, you might have the engine number as a label, or the wheel number if you're actually tracking something on the landing gear. They all could be in the labels, right? And later on, when we go a little bit deeper into the functions, you'll see that those labels are used at different points in the data flow to select the data you want or to group data and actually act on groups of data, on equivalence classes of the data based on the labels. So each geotime series is identified by its class and labels, and we have another set of key values which can change during the lifetime of the time series, of the geotime series, right? Labels are immutable because if you change one of the values of the labels, you're basically identifying another time series, right? But we have another set of key values, which are called attributes, which you can make evolve during the lifetime of the series. So we support different time units, ranging from milliseconds to nanoseconds. We have customers in the high-frequency trading business, and they're eager to have nanosecond precision, right? Macro is just too coarse grain, so they can't handle that. Yeah, I know. On the other side, we have some customers that say that real time is the next day, right? So it's kind of a wide range of notion of real time. We support 4 types that you can actually put in those sequences. So 2 numeric types, long and doubles, 64 bits signed, so you can put lots of values in that. Booleans, because we have lots of switches, for example, that you want to keep track of in a very concise way. So we support Booleans, and we support strings. It means that basically anything could be the value of a time series that you can track and analyze using Warp 10, right? We have people who actually pack images that are encoded as strings and use that as the value of a time series. Or ourselves, we have an inception process in which we take a time series, we pack it, and we put it as the value of a time series. And you can do that until you go in limbo, right? We support full Unicode for strings in values, for labels, and for classes and attributes. So you can put Chinese, Japanese, Arabic, Hebrew, whatever in the name. You can even put spaces if you want, if you're really vicious. So no, that class is 3 spaces. You put 2. That's normal. You're not getting the right answer, right? So we support that. We support for the geo part a precision in latitude and longitude, which is around 1 centimeter at the equator. And for the elevation, the platform actually considers that the number you're giving is in millimeters, right? So you can track pretty precise stuff using that platform. The geo part is obviously optional, so you can just have regular time series without the geo metadata associated with them. Okay, so a little bit of architecture of our platform. So we have several versions of the platform, which comes in various sizes. So medium to large. So size really refers to the amount of data and the amount of requests that you can actually handle. So medium to large, we're talking tens of millions of series, right, which is in the lower end of what some of our customers are actually doing, and a couple hundred billions of data points, right? So small amount of data by our standards. Right? And you'll learn to have those standards, you'll see. So we have a standalone version which is backed by LevelDB. LevelDB is a library which is made by Google, which handles SST files, so sorted string tables. And basically, it's a log-structured merge tree, and you can just push data with keys, and you have the ability to actually retrieve those keys by scanning a key range. So this is really suited for time series data. So the standalone version is standalone, or it can have siblings. So you can actually make it work with other instances of the standalone version using a mechanism that is called data log. So you can actually move data from one instance to the other. And we're also in the process of adding sharding to that, so you will be able to shard and replicate using the standalone version of the Warp 10 platform. It works on a laptop like that. It has poor performances, though. It tops at around 75, 80,000 measurements per second, right? So we call that poor performance, because if you're in the distributed version, which is the next one we have, so that size XL and above, you can scale to millions of data points per second. Basically, we are built around Kafka and HBase. So we use Kafka as a buffer between the ingress layer and the actual storage layer. So anything that goes into the platform goes into the ingress component that you have here and is dumped into Kafka and then consumed later by another component, which is called store, which will store it in HBase. So HBase, for you who don't know what it is basically an open source implementation of Bigtable running on top of HDFS, right? HDFS being an open source version of the Google file system. So all that is part of the Hadoop ecosystem. I'm sure you've heard about Hadoop. If you haven't, please leave the room. No, I'm kidding. No, I'm sure you have heard about Hadoop. Hadoop is a yellow elephant, and there are lots of big data infrastructure that rely on Hadoop. So for the distributed version of Warp 10, we rely on HBase, which basically gives you unlimited scalability by adding servers, right? So you start small with 5 or 6 servers, and as your data needs grow, you add servers, and you can scale to trillions of data points, hundreds of millions of series, and have all that data actually available for analysis. The distributed version, so you are in a circle, they can each be scaled out. So we could have 20 ingress, 30 egress, 50 stores, 20 directories, whatever. And depending on which one is actually the weak point, you can just simply replicate that and have a scalability that goes to what I've said earlier, millions of data points that you can ingest per second, and really no real limit in the amount of data that you can handle. So that's the XL version. And then we have a small version. So we have what we call the embedded version, which is really the standalone version running on embedded hardware, such as the Raspberry Pi. So you can deploy the Warp 10 platform on a Raspberry Pi, benefit from all the analytics on that little platform, and actually embed that platform into a device. So today we have people embedding the complete Warp 10 platform on the edge, on heat pumps, on power generators. We're looking at integrating into sensors that take videos and analyze the video on the edge, right? Because you get all those benefits of that analytic system directly where the data is actually collected. Without the need to have a network, you can take decisions on the spot. And that's really a trend that we see. You've probably heard about fog computing or edge analytics. That's really what we're into here. We're kind of realizing that relying on the cloud for performing analytics on data that comes from sensors is good when you have good connectivity and you know that the data can flow seamlessly from the device to the cloud, and then you can take all your decisions on the cloud, right? If you send a device in the wild and you actually negotiate a data plan with a carrier, it's going to charge you around a minimum of $5 per megabyte of data that you actually transfer. So you don't want to transfer too much data, right? You want to keep your decisions and your data locally, and as much as you can, not rely on sending data out to take decisions or to act upon your system. So the embedded version is really, really nice for that. Between those three versions, what you have to know is that the only thing that differs is the backend used for storage, right? We have exactly the same capabilities in terms of analytics on all those three versions. So whatever you build on the distributed version, whatever algorithm you actually implement, you can actually deploy that in the embedded version too. So we have a few APIs to interact with that platform. The first one, obviously, is how you actually store data. So there's an endpoint which is called API v0 update to update the database. And you're just pushing data in a very simple text format. So you're going to specify the class and labels of the series you want to update. You're going to specify the timestamp. In an optional way, you can have the geo elements and then the value. And then you push that data to that endpoint, and it gets taken care of by the platform, stores it where we want, etc. We also have a WebSocket that you can use where you can actually push data as a stream. When you're looking at the update endpoint, not the WebSocket one, you can push as much data as you want. You're not limited to 10,000 data points or 1 million data points. You have 3 billion data points you want to push those 3 billion data points. We're not materializing anything in memory. We simply stream those directly to the backend layer that does the storage, right? So you can push historical data in a single request and not worry about it. For multi-tenant deployments, we also have throttling mechanisms. You don't want people to actually produce, 3 million data points that belong to 3 million different series by mistake. So we have a mechanism where you can say, well, okay, as a start, you're going to be able to create 1,000 series, and then you're going to push so many data points per second as a top limit of your interaction with the platform. So that's really useful in environments where people are not really used to time series data, and they actually do mistakes in terms of the way they actually model their data, and sometimes you see weird things, like people putting timestamps in the labels. So if you think about what I've said earlier, if a value of a label changes, then it's a new series. So basically, by putting the timestamp in the label, they're creating series, lots of series, that have a single point, which is not really a series, right? Another endpoint we have very few of them, is actually retrieve the raw data that we pushed into that platform. So we have a /fetch endpoint for that. You can retrieve the data for a specific set of series, which is a selection of series based on regular expressions on the labels, attributes, and classes. So that's where the modeling of your data actually starts to make sense, right? You want to get all the data related to the left wing engine. Well, you're going to have a label that specifies which engine is the left wing engine. And you're going to just select the series that are related to this particular aircraft for the left wing engine. What you have to know is that we will give you back the exact data that you pushed. And why am I saying that? Is that because some time series database systematically do an interpolation. So they will return a value which is in between two values that you pushed, because the system actually considered that 3 values should have been returned, but you only provided 2, so it's going to infer the third one. But that's not the real value that you actually pushed initially. Another endpoint that we have is similar to fetch, but only concerns the actual metadata of the series. So you just want to retrieve the list of series that match specific criteria. And usually you do that to actually work with another endpoint which allows you to modify the attributes. So you're going to retrieve some series that contain some labels or attributes, and you want to change some of those with different attributes later. So you do a find, and then later you do a meta call. So the meta call is there to actually set the attributes for geotime series. And by using attributes, you can actually set up some pretty complex lifecycle management for your data. So 2 examples, one in monitoring. So who has done monitoring before? Systems, right? So when you monitor systems, usually what you do is you look at metrics, and according to some rules or some computation you do on those metrics, you decide that a system is actually faulty, right? And what you do if the system is faulty is that you trigger or you configure something differently than it usually is at the first time. And you usually do that in a single unit of work, right? By using attributes, you can actually separate the concerns. So you can have a script which will look at that condition you're looking at on your metrics. And if it detects some series that actually have that condition, it's simply going to mark those series using a specific attribute. And on the side of that, you have another script that actually only looks at series that have that specific attribute. So if currently no series has that attribute, then it has no series to work on, and no work is done, right? If it has a set of series with that attributes, then it will take care of those. But that means that basically you can have a contract between the script actually doing the action based on the presence of that attribute and the script which is actually issuing that attribute, right? So you can separate the two, have 2 different teams actually working on those synchronously, and you'll do good. And that's going to be way more flexible than have everything in a single unit of work where you're going to actually check the condition on your series and act upon your system to fix this condition. So you can use attributes for lifecycle management. Also, you can mark series that need to be deleted, for example, and then you can actually later call the delete endpoint and only delete those series that need to be deleted, right? You can also geographic information to the attributes. So that's not you shouldn't be confused by that part, because it's not the same as the geolocation of the values, right? The values have a location associated with them, and that only makes sense if the value is actually on a moving sensor, is taken by a moving sensor. If your sensor is fixed on a wall, then it still has a location, right? But that location doesn't change. So ideally, you're going to put that location in the attributes and not for each value, because otherwise each value will have exactly the same geographic location. So even though we're pretty efficient at storing that kind of data, it's a waste of bytes to actually do it. So put that into the attributes using, for example, GeoHash, or we use HH code, which are internally supported by Warp 10. We also have a delete endpoint, so that seems odd to actually mention it as the API as something important, right? But it is important, because in some geographic areas, like Europe, for example, the laws require that you provide your customers a way to delete their data. So it's a regulation, you have to provide that, right? So that's one of the things you have to think about. The other point is that deleting data produced by sensors can rapidly get out of hand. Imagine you're actually tracking data for servers, right? So you have 10,000 servers actually pushing data to your platform every 30 seconds, lots of different sensors. The speed of the fans, the temperature of the CPU, capacity on the disks, memory, et cetera, et cetera. And after 6 months, you say, well, you know what, that data, I only need it for 6 months, so anything older than 6 months, I'm going to delete. Okay, so you mark something, think about deleting data after 6 months. But you forget to do that after 6 months, just do it after a year. So now you have to delete 6 months of data for 10,000 servers with maybe 100 sensors each, bringing back data every 30 seconds, right? That's a lot of data. Well, we can handle that. We've had customers actually delete 2.5 trillion data points over the course of 1 week. So 1 week seems like a lot of time, but that was at an average rate of around 7 million delete per second for a week, while still writing about 1.5 million data points per second. So you're basically adding 1.5 million data points per second and deleting 7 million at the same time, right? So the delete endpoint is by itself a whole project, and it was actually quite hard to do. Especially, for example, since you don't want to hotspot your storage layer. So if you're deleting 100,000 series, you have to make sure that you first shuffle your series so you're not deleting a range of series that are stored on the same server at a given time. Otherwise, you're going to pound that server. I mean, it's like, you know, firing with a bazooka on that server. It's going to die. So you can't do that, because if that server actually dies, then you cannot push the data. So people who expect their data to be available within several milliseconds start to get upset. So that's the kind of stuff you have to think about. And then last, I think the most important, and that will take most of the rest of my talk, is the analytics endpoint. So the idea of storing time series data is not to store time series data. It's really to enable value creation out of those data, right? You're measuring things in a building, you're measuring things on a car, you're measuring things on an aircraft. What you want to do is actually get some meaning out of that data. So this is what the exec endpoint actually allows you to do. It allows you to post an analysis script which will get executed as close as possible to the data, and which will return the result of that analysis as a JSON object that you can actually insert wherever you want. A web page, a mobile app, desktop app, a server app, whatever. It's not a real query language, and we hate that terminology because a query language is there simply to query. So you're querying some data. So give me something which is pre-existing. Very well. Well, you're not going to go very far with that, right? Problem is that most of the solution of time series have a... They can allow you to retrieve data which is available on the back end, maybe do some very simple computations, and that's about it. Well, what we created is something that enables you to do complex analysis. So for example, you're measuring sound levels or you're measuring vibration levels and you want to do a Fourier transform every 2 seconds and actually store the spectrum as a result of your Fourier transform and compare those spectrums over the course of 3 months. Well, you can't do that with a query language, right? You're going to have to write some code outside of the platform to actually do all that stuff, and that's going to cost you lots of time because you're going to have to invest time in thinking about how to structure your data, how you're going to code your algorithms, maybe take a library, an existing one, and insert it into the platform. That's not efficient. Well, we provide that off the shelf, so we've got Fourier transform, wavelet transforms, lots of other stuff that you can simply request to use. So in that sense, our language is way more than a query. Rapidly, we have streaming endpoints for pushing data and for consuming data. I'm not going to go over that. In security, we also have a few things. So we have an authentication mechanism platform which is on crypto tokens. So basically, we have tokens which bear what labels you're going to attach to the series, which bear what data you can actually access, which optionally can have code that is attached to them, which will transform the data on the fly, retrieve the data. So you think you're retrieving raw data, but you're really retrieving a transformed version of the data. Imagine how that works. You can obviously revoke the tokens whenever you want. So it works really as a powerful way of giving rights to people for a limit. So for example, you could have a call center and the agent in the call center needs to see the data for the caller for a very limited amount of time. Well, we issue a token which is good for 2 minutes. And during those 2 minutes, the data can be accessed. Using that token, if you put it aside, after 2 minutes, it's gone. You can't use it anymore. We also have mechanism for encrypting data. So we have encrypt the metadata, so the class labels and attributes of the series by default. But we also have an option to actually encrypt every single data point that flows into the platform, right? And some customers actually require that. Not many of them, but some of them do. We can have SSL support by having proxies such as Nginx or HA proxy in front of the Warp 10 platform. So you can have a secure channel between your devices and the actual platform where the data is stored. And we have integrity checks in the distributed version of the platform between the various components. So you cannot have a rogue individual actually pushing bad data into the platform. It will get discarded, right? So that's for security. And now, analytics. So as I've said, what we've built on analytics is way more than a query language, right? It's a language which was inspired by two things. The first one being the HP calculator. I don't know if, maybe you're too young to have used that, man. I don't know. I love that. It uses the reverse Polish notation. It has a stack. You can play with that. It's fun. Grab one on eBay and play with it. You'll love it. It has a 4-bit processor. Yeah. You can really do stuff. So that was the first source of inspiration. Second source of inspiration was the PostScript language. So have you ever used the PostScript language? It's basically the language that was created by Adobe to talk to laser printers. Well, as it turns out, it's a complete language where you can actually do stuff. So the anecdote I'm going to tell you might not be meaningful to you now because your watch is probably more powerful than any computer I had back in the days when I was in engineering school. But when I was in engineering school, in some rooms, the most powerful machine in the room was the printer. It was really powerful because you needed a very powerful processor, CPU, to actually do stuff, to print a page on a piece of paper, right? So when we realized that, we actually thought that it might be fun to use the printer rather than the computer. So basically, we were actually doing lots of stuff in PostScript, directly executing on the printer and getting the result back, right? So you could actually compute Mandelbrot set on the printer and would perform tremendously faster than the computer you were actually displaying it after. So that was another source of inspiration. So warp script is a stack-based language. So basically, you push stuff on stack, you execute functions, they modify the stack, and you pass on to the next function. It's dedicated to series analysis and geotime series analysis, which means that we have a whole bunch of functions that are tailor-made to actually render things simpler with that kind of data, right? So the way it works is after your execution, you will get a JSON object back, a JSON array, really, of which each element is the level of the stack, right? So if you left three things on the stack, you will get an array of size 3 with the 3 elements that were on the stack. Whatever you leave on the stack can be complex objects. It could be a map, it could be another array, it could be geotime series, lots of stuff. Only working with the stack is kind of cumbersome, so we variables, so you can define meaningful names and reuse that throughout your program. A nice thing that comes from PostScript is what we call code serialization. So basically, data is code and code is data, right? So you could dynamically build a string which is code, which is valid warp script code, and execute that within your code. So basically, you can on the fly generate code, or you can template your code, replace stuff in the template, and have that being the code that you're going to execute, right? Which also means that you can actually passivate your execution units, so you can store the state of the stack and your code somewhere, and maybe later restore it and continue execution where you left it. That's also possible. We support complex constructs, so we think that warp script is actually Turing complete, so you can do anything you want, including the game of life or stuff like that. You can do it. So we have loops, we have conditionals, we have macros. We'll go a little bit deeper into that. We also have secure code execution. So when you deploy a version of the platform, it has a special key which is to validate encrypted code. So you can ask the platform to encrypt some code for you. It will give you basically a blob of data that is meaningless for you as a user, but which is meaningful for the platform because the platform knows how to actually access the code which is inside, right? So this is very interesting because you can actually deploy code on mobile apps without exposing sensitive information, right? Because you're basically encrypting the code, so nobody can actually see that, and only the platform you're talking to can actually decrypt the code. And overall, since we're using a stack, we are very well suited for what we call a data flow model. So basically, you have data, you pass it into a layer which does a transformation, which produces an output, which goes into as the input of a next step, et cetera, et cetera. And we'll see later how we leverage that to actually move WarpScript way beyond what we call the interactive Warp 10 platform and to other environments such as batch and streaming. So at the top level of WarpScript, we have 5 frameworks, what we call frameworks, which are common operations that you do on time series, right? When you collect data from sensors, the first step is to collect the data. That means read it from the electronics that is your sensor and bring it somehow to a platform which will store it, right? That's the first step of whatever you're going to do. The second step usually, and many people don't think that this step is actually something that has to be done, is what we call alignment of the timestamps. What is that? Well, if you're actually measuring timestamps with a microsecond precision, there is a very tiny chance your timestamps are actually the same between 2 series, right? So if you want to compare or if you want to work on several values from several series that were about the same time, you first need to make sure that they are indeed the same time, not just about the same time. So that's realigning the ticks, right? Making them at regular intervals so you know that every single series that you're working on will have the same ticks. It's no big deal if you actually shift a value from a few microseconds to another value, right? It's within that second, it's still that value that was measured. So we have a framework for that, which is called bucketize. We have another framework to actually slide a window on a series, which will apply a function on the window and produce an output series out of that. We have another framework which is called reduce, which takes multiple series and reduce them into a single one. So for example, you want to do a computation that computes the average temperature of a set of assets. So you're going to get all those assets, you're going to align the ticks, and then you're going to say, I want the average temperature timestamp by timestamp. The reduce framework will allow you to do that. And then we have filter, which, as its name implies, allows you to filter series based on various criteria. So name of class, regular expressions on class, regular expression on labels, filters on values. You only want those series whose standard deviation over the period of, that you're actually looking at is above a threshold. You can do that with filter. And then apply, which is a generic NRE function that you can apply to series. So basically, it's a function that takes as input n parameters where each parameter is actually a list of series, right? So it seems complicated at first, but basically you can take a set of series and say, I want a resulting series, which is the first one multiplied by the second one divided by the third one, and a Boolean indicating if it's above the threshold that is stored in the fourth one, right? And you can do that in one call, simply by defining a function. And then for each tick, we're going to look at all the values, and we're going to apply that function to those values, and we're going to get a result which will be true or false, and which will be the result of the apply framework on that set of series. So on top of those 5 high-level frameworks, we have a few functions. I'm going to go through each of them. I'm kidding. So we have 800 functions right now, ranging from summary statistics to anomaly detection, Fourier transform, signal processing stuff, statistical tests, encryption, key generation, lots of different things that are meant to make your life easier when working with time series, right? This is why we're far away from a query language, right? That's way more than a query language. So Warp script is pretty complete when it comes to expressing stuff you want to do. So this is an example. I'll give you the slides so you can look at them afterwards. But basically, that's an example of typical stuff you do on time series data. So the first one you do is actually fetching the data with a set of credentials and a selector on various elements of the metadata, so the class and the labels. We're going to remove the resets. So what's the reset? Imagine you have a counter, and when you reboot your machine, your counter goes back to 0, right? So you're going to have a graph that goes like that, down to 0, back up, down to 0, back up, etc. You can't compute rates or deltas with that at the point where the counter reset happened. So you have to get rid of the resets. Well, how do you get rid of the resets? Well, you can write a function that gets rid of the reset, or you can use Warp script and just simply say reset. I want to get rid of the resets. So the fold means that we're not taking care of resets of counters that are usually decreasing. We're taking care of counters that increase, right? So basically, instead of having a graph that goes like that, you're going to have a graph that goes like that, because we offset the values after the reset to the one that we read plus the last value that we know before that. Then we do in the ticks, and then we're going to sum by host name, which is one of the labels of the data, I guess. We're going to fill the gaps, because you might have gaps in your data, right? So we're going to fill the gaps in a specific way. And we're going to compute a rate on that data. That's all explicit. You can have comments. People can actually read that code, and you're going to understand it, right? Well, if you're using a query language, chances are people have replicated somehow what SQL looks like. So who knows how to put comments in SQL? Oh, bad news. Usually, there's at least one person that answers, and then my next question is, okay, do you do it? And usually the answer is, well, in Warp script, You can easily put comments so people can actually maintain your code, right? And it's really important. Because after some time, you're going to have lots of code to analyze your time series data, and you don't want that to be just a bunch of SQL-looking queries. So if you're not satisfied with those 800 functions, which we're not, we always add some new ones, so you can extend warp script in different ways. The first way you can extend warp script is by writing macros. So macros are basically pieces of warp script code that you deploy on the server side and that you can later trigger. So you have someone write something awesome, ask them to do a macro, deploy it on the server side, and then everybody can use it, right? You can also deploy them in a jar. Quam said warp script is actually written in Java. So you deploy them in a jar file and have them available to another deployment of warp script. The second way of extending warp script is through what we call extensions. So extensions are basically Java classes that will either remove functions. So that's not really an extension, but well. So you can remove functions. You can modify the behavior of functions. So on April 1st, if you want the divide to actually be a multiply, you can do that. And you can add functions. And that's really easy. So you can write extensions for doing whatever you want. Let's say you have a system, an existing system that takes as input some data. You want to make it available through warp script. Just write a simple extension, and that will become another function in the language, and it will be available to people using your platform. So it's really, really easy to do that. And by doing that, you can actually do one thing which is really interesting, is to connect to an external data source. So we're never competing on performance of data storage, etc., because we know that warp script can actually talk to any data source out there. So you want to store your time series database in MySQL? Fine, do it. We don't care. We can read them from there. You want to store them in CSV files? We can handle that too, right? It's just a matter of writing the right function that will fetch the data. And then once you do that, so basically you write two functions, one to read the data, one to write it. Once you do that, then all the 800 functions of analytics are available on your data, right? So you can use whatever time series database I showed on the earlier slide and apply warp script code on those. Then we have another way of extending warp script by calling external programs. So you're not fond of Java, fine. Actually, I didn't change the color, but there's something written here, but you can't see it. But 3 simple lines that tells you how to actually call that. So if you're not fond of Java, but you prefer Fortran, for example, and you've got code that does some very advanced analytics in Fortran, well, you can call that. You can call that from warp script. Simply write a wrapper, have your Fortran code actually read standard input, do its stuff, and emit something on standard output. And we'll reintegrate that into warp script. So you can call anything. We use that to actually call TensorFlow and apply models on time series. So basically what we do is that we extract features using warp script. Then we call TensorFlow to apply the model, to evaluate the model on the features that we created. And we get the result and continue in the data flow model after that. So lots of different ways you can actually extend warp script past those simple 800 functions. Okay, now the sugar. Lots of people think that what matters in time series analytics is actually visualizing stuff. It's true that it's important, but you shouldn't start by this, right? Because if you don't have the data, if you're not managing the data, if you're not able to actually compute stuff on the data, what are you going to visualize? Nothing really interesting, right? So you should focus on the actual analytics first, and then find a way to visualize that so your end users are happy. So we have a few tools that we integrate into Warp 10 to help you visualize stuff. One thing we learned is that you shouldn't consider that you can have a generic layer of visualization, because every single vertical usually has some habits of visualizing data in a certain way. So you cannot say, oh, you know what, I'm going to do that widget and it's going to fit everyone and everybody's going to be happy. That's not going to be true, because people in the energy business will expect something, people in aeronautics will expect something else. They're all different. So we came up with a set of widgets that are bare bone, basic level visualization. They enabled you to actually display stuff, but they're not pretty in any way, right? And then they're not meant to be. There are lots of people that do that way better than we do. So the first thing we have is what we call the quantum web components. So they're web components are enhancing the HTML language, so basically adding new tags that you can use in your HTML page. And the philosophy that we've had with those tags is that between the opening tag and the end tag, the only thing that's going to appear is going to be warp script. So you can focus on your analytics and not on the plumbing around it. So no JavaScript, no thinking about how call that function, have a callback, do my request to the server. It's all taken care of by the widget. The only thing you should focus on is the warp script in the middle. And the way it works is that the warp script in the middle is called by the widget, so it's pushed to the platform you actually specified, by first adding a few parameters, such as the width in pixels of the div in which you're going to display something, the height, maybe other parameters, and it expects, as a return, the stack on in a certain format. And if you respect that format, then the widget will happily display whatever series you actually sent back. So you can focus really on the analysis part of the job and not on the plumbing. So you can display graphs. You can display graphs and maps, obviously, because we actually do geotime series. And we can display images, and we'll come back to that a little bit after. And part of the use cases of the quantum web components is what we call our quantum IDE, which is basically a window where you can type warp script. When you press execute, you can see the JSON resulting from your execution. And if there are geotime series in your result, then you can actually plot them, right? Very easy to start working with your code and get up to speed with warp script. Those are for simple graphs, so you can display trees very, very easily, but sometimes you need to do more, right? You need to display things that are more complex, that are more elaborate, and that show data in a way which is closer to what your end user actually expects. So that's the case here, for example. So this graph here, this image, shows you a heat map of pairs of values which are speed and altitude of aircraft, right? So on that graph, there are 3 million pairs of speed and altitude of aircraft. This image was actually produced by the code on the left. So it's rather concise, right? Why? Because we took a language which is called processing. I don't know if you know that language. It's a language which is used by, most notably by artists to actually do graphical installations. So they can actually produce art on a computer by using that. So we integrated that language directly into warp script, so you can actually work on images and produce images in a programmatic way in warp script, right? The interesting thing is it's really concise. So we're actually cheating a little bit here because we have a few macros that we're relying on, but still, it's rather concise. And it's fast. It's really fast. Actually, fetching 3 million pairs of data and producing that image on my laptop here takes 18 seconds, right? We tried to do the same thing with a script which is called heatmap.py, which does the same thing in Python. We stopped it after 6 hours because it didn't produce the image, right? That took 18 seconds or 18.5 seconds, I think, including the fetching of 3 million pairs of data points. We also have integration with third-party tools. So we have a plugin for Grafana. We have a plugin for Kibana. because there are some people doing monitoring that like to use those tools. So we have plugins for those tools so they can actually fetch the data from Warp 10, and you can benefit from the analytics that we have in Warp 10, so you can display that in those monitoring tools. Okay, so that's a description of Warp Script, and what I've covered so far is what we called our interactive platform, right? So we have an execution engine for Warp Script, which you can talk to. You can push a Warp Script code, it will get executed, and you'll get the result in JSON that you can integrate into your existing application. But that's just one part of the story, right? That's one part of the story because at one point, what you will want to do is go to the next level in terms of analytics, right? Doing interactive stuff, ad hoc querying, ad hoc computation is fun, but it only leads you so far, right? After usually 1 month, 2 months of data, you want to start looking at those 2 months of data. You want to start analyzing those 2 months of data just the way you analyze the last 5 minutes, except you have 2 months of data. And you have 2 months of data maybe for 10,000 servers or for 100,000 sensors. How do you do that? You cannot rely on the analytics engine that loads everything in memory to do that. It's not possible, right? So if you listen to people, they will tell you, well, you know what, I have sensor data, I have time series data, I'm using Spark to do analytics on those, and it works well. Well, usually if they tell you that, they haven't tried it. Or they haven't tried it on massive amounts of data, or on massive amounts of data they might have, but at least not on complex analytics, right? So they didn't compute Fourier transform on their data. Maybe they did something very complex called an average, and I'm not even sure, or a min, or a max, because actually coding a Spark is not that easy. Imagine you have a series which is 3 billion data points long, it doesn't fit in memory. How do you compute a moving average over windows that span, I don't know, 37,561 data points? How do you do that? Well, you have to re-engineer something. You have to think about it. You have to write custom functions available in Spark and that you're going to be able to use after maybe 2 months of development, right? That's not worth it. Maybe you want to do that computation only once, right? So what can you do about it? Well, the way we solve that problem is that we said, you know, we have that language to actually manipulate time series data. Why not make it available in those tools such as Spark, Flink, Pig, that actually work on a very large scale? So that's what we did. We made sure that we could use Warp Script, the full language, the full 800 functions, the extensions that you've coded, right, in a batch mode. So working on all the data you have stored from your system. So the way we did that is that we took very popular batch analysis frameworks such as Pig, Flink, Spark, that run on top of Loop, that can run data in various environments. So we built a component so it could actually talk to Warp 10 and fetch data out of Warp 10, but you might also be able to data from files that reside in HDFS or in different storage layers. And on that data, you can use the full power of Warp Script, right? Without having to reinvent the wheels. That's really our philosophy. There's not enough time to be wasted redoing that. Especially since, no offense, you're not going to do it as well as we've done it. Because it's our business, right? We sell support to people who actually make money using our solution. So we made sure that we made it the best way possible. You're not going to do that. You're going to do an ad hoc code for a specific one-shot computation that you have to do on your data, and you're going to throw it away after, right? We don't want you to do that. We want you to spend your time engineering your Warp Script, not reinventing it. So that's what we did. We integrated Spark and Flink, and we add functions so you can actually, well, you'll see it in the slides, but basically you can structure your data and then pass it stack on which specific code will be executed. And after that code is executed, the return of that execution will be pushed into the batch analytics framework, right? So you can benefit from the complete set of warp script functions from within those environments. And same thing in streaming. Once you have data flowing in from sensors, at one point you're going to say, oh, I want to take that decision on the fly. I want to trigger something if I detect that the moving average over the last 5 minutes of this and the Fourier transform of that over that window are in such a way that it's meaning something for my use case, and I want to take action upon that, right? Well, same thing. If you think that off-the-shelf streaming analysis frameworks will do the trick for you, you're wrong, because you're going to have to write lots of code. So there again, what we did is that we integrated warp script directly into a few frameworks so you can focus on your problem and not on the tools to actually solve your problems, right? So, for example, in Storm, so I don't know if you're familiar with Storm, but basically Storm is a tool that was done by a company called Backtype that was later bought by Twitter that allows you to define what we call topologies, which are basically nodes sending data back and forth between them and taking action, doing transformation on those nodes, right? So if you think about it, really what that is a data flow model. So you're making data flow from node to node. And remember what I said earlier is that that's exactly the same approach we have in warp script. So basically, you can define nodes where the action of the node is actually transforming its input data into an output. And you can do that with streaming data on the fly. Data flows in, you act on it, transform it, push it down, somebody else does something else, and your system is live, right? And on the side of that, you can also store the data into Warp 10 and then later do also some batch analytics on it. So, use cases for that. Well, there are plenty. So far, Warp 10 has been used for many different things. So even though we don't advertise it as a monitoring solution, we have people who actually used it as a monitoring solution, and at a massive scale. So to give you an idea, we have customers that actually use it on several 100,000 servers, gathering data for more than 300 million metrics, and having historical data that is in the tens of trillions of data points. Right, that's a lot of data. Warp 10 was also used on smart grid data, so what we call synchrophasor. So they measure phase and magnitude of voltage and intensity of the current at various points in the network, and by looking at that data, you can your actual electrical grid is under stress, if it has problems with islanding between different parts of it. So all that is time series analytics. It has also been used to track the latency of packets in telecommunication networks. It has been used to make available weather forecasts, and lots of different things in many different areas. And the interesting thing is that all those use cases were actually done using the exact same version of the platform. So we don't have a Warp 10 for aeronautics, a Warp 10 for smart grid. It's all Warp 10, right? The open source Warp 10, and then it's just your creativity and your intelligence that you put to work with those tools, and that will lead to a great solution to your problem. Okay, so 3 steps. Again, you'll get this. I'm not sure you get the slide, so you can actually get that working. 3 steps to actually deploy the standalone. You do a curl that will download the archive, you untar it, and then you start one script, create the storage layer for you, and launch the daemons. Launch the Warp 10 daemon and launch the website that contains the Quantum IDE, right? Once you have that, you will see it will display you what tokens you can actually use to interact with the platform, and you'll be able to store data and start playing with your data. That's very easy. After that, if you want to go one step beyond and actually go to the distributed version, then it's another story. You have to deploy Hadoop, you have to deploy HBase, Zookeeper, Kafka. It's a little bit longer. You cannot automate that the same way. But first, play with a standalone version. You'll get a great deal of things done, and you'll have fun with the Warp script language. We're actually working with Squam so we can offer a project around time series and analytics. So we'll see how that goes, see what we can come up with. Some fun stuff to actually do. Please do not rate my session because you can't, right? Because those slides were taken from a conference where you could actually rate the session, but you can't. And I'm available for questions, so we can actually have questions now that will be recorded. Or if you're too shy to actually have your question recorded, then you can ask it later. I'm here. I have a meetup at Facebook in around 6 o'clock, but until then, I'm available. What about what?
Your hair.
My hair? Well, I kind of, my hair grows and I actually cut it when it takes me too long. I look at the time series of how much time it actually takes me to get my hair wet in the morning when I need to wash it. And when that goes above a threshold, I have my hair cut.
Is there a warp script for that?
There's a warp script for that. Yeah, I'm sure we could figure it out. Yes?
So you joked about sub-nanosecond time series. I wondered, is that real, or where is the demand?
Oh, I joked about nanoseconds time series, but I was not joking. Actually, we have a company we work with that actually measures timestamps on network packets. And their network gear, which are, I think, Arista switches, they give them timestamps which are accurate to 3 nanoseconds. So it's not a joke. I mean, some people really need to have that kind of precision at the storage level. It doesn't mean that their clock is accurate at 3 nanoseconds. It just means that between 2 ports, for example, in a switch, they can measure timestamp, and they know that they can have a difference which is as low as 3 nanoseconds. Yeah, that's basically measuring latency in packets in a network. So basically, you have a packet that goes out of a network interface at a specific time. So you look at the time, you look at the fingerprint of the packet, and you look at the same fingerprint of the packet on the other side of the link, and you compare the timestamps. And that gives you the latency over the network link, right? Yeah, we actually had a customer that used it for analyzing patterns of access to DNS servers by looking at density of calls to specific domains or from specific areas. So yes, definitely. It can be put to work on anything that can be represented as time series, and we personally think that that's more than 95% of the data out there. Which you haven't started yet using, right?
No. One of my favorite talks at the Bitcoin conference I went to was this arbitrage company on smart grids, specifically in Texas.
Okay.
So I was wondering if you provide to companies like that, and more specifically for you, what do you feel about the public blockchains and database storage?
So we work in the smart grid business. We actually won a challenge in December that was organized by General Electric. So it was the General Electric Digital Industry Challenge, and we specifically won the one that was on massive time series management. I wonder why. So those data were synchrophaser data, so data coming from smart grids, on which they had problems for storing the data in a very compact form, but also on having tools to analyze that data. So that's one thing. In terms of the second part of your question about blockchain and that in the energy business, to tell you the truth, right now, I don't think we're yet at the point where that's going to be useful, because where I see that being useful is when you're going to have lots of small producers, and you're going to have smart contracts between those producers, but we're not there yet, at least not in Europe. I mean, in Europe we have, one giant producer in France, for example, and maybe some people producing electricity for themselves, but very few at the city level, for example, very few windmills producing electricity for your neighbors or solar panels for another set of neighbors. So we'll see how that evolves. As part of the GE Digital Challenge, there was a challenge on the use of blockchain in energy business. So another company actually won that. We were not in that part. So I can put you in contact with them if you want to ask questions. They might be able to tell you what they've done and what their vision of how that's going to evolve is. Anything else? No? Well, yeah.
Could you adapt this to space location beyond just geolocation within our little globe? Can you extend longitude, elevation?
We could probably do it. Well, we could easily do it around another planet, right? Because if it's spherical, that would be easy. Otherwise, yeah, basically, if you have X, Y, Z coordinates, then yes, you can probably use it. It might not be accurate enough, or you might not have enough bits to actually store, very distant objects. But we can think about clever ways to actually make that work anyway. And you always have the option of actually using several time series, even though that's not the right way to do it in our sense. You could always do that, and then yes, you could actually locate, distant objects. Yes. Well, the company is around 10 people, and then we have external contributors on GitHub. So we have people, contributing from some of our customers and from people just using the tool and not paying us anything.
You do the main job.
Yeah, we do the main job. Yeah.
Yeah, I'm wondering what's different or special about time series. Like, it seems that you could equally well apply this to like a sorted list of credit card numbers or some of the just massive block of data. Is there something particular about the time format?
Well, the things you do, which are handled by the 5 frameworks I listed at the beginning of the Warp script presentation, this is something that you will usually not find in credit cards. For example, credit cards, you're not going to average the credit card number, right? That's meaningless. So usually you're going to do something which is, there are some cases where you could actually manage credit card numbers as a time series. For example, to see a merchant and see if you have returning customers, for example. Well, actually, by regulation, you're not allowed to store credit card numbers like that, right? So I'm gonna, but you could hash it, something that derives from the credit card number. Well, it's a sequence. So basically, whenever I said time series, you could really think sequence of things. That's why we say that at least 95% of the data out there is really, time series or time series-like, if you look at sequences. What is really specific to time series and machine data, more specifically, is the fact that once you open the flow, it never stops. Never, ever. And when you have a factory floor or a smart grid pushing you 1 million data points per second, that's going, and that's just going to increase. If it falls down, then they're having a problem, or your network provider is having a problem. But it's totally different than data which is produced, credit card numbers, for example. They would probably be, time series or sequences, but they will be very low in terms of number of data points. Why? Because as an individual, the average number of bank transactions that you do in a year is probably around 2,500 per year, right? If you look at sensors on a synchrophaser, they're at 400 hertz. So 2,500 data points is like 6 seconds of the life of that sensor, compared to 1 year of the life of an individual. So the main difference with time series data compared to the other one is, one, the pace at which the values actually flow in, the need to actually keep those data, usually for a long period of time. Because if you're looking at whatever data coming from time series in the city, for example, you need to have at least 12 months of historical data. Otherwise, you won't see the effect of winter or the effect of, the Super Bowl. So you need lots of data to actually have meaningful stuff that come out of it. And that takes lots of room. And you need to store that data, but you also need to make it available for analytics. So you need a system that is able to ingest it, able to store it, and make it available for analytics in a reasonable amount of time. You don't want to wait 2 hours to actually get the data from the past year before you can actually get something out of it. You want it rather fast. So that is really different in terms of storage. And then in terms of analytics, you've seen all the 800 functions I had on that slide. They're almost all specific to time series data. If you don't have those in your toolset, in your toolbox, you're going to have to rebuild them. And that takes lots of time. So that's why you need specific tools for that kind of data. And then you can enhance those tools with some stuff that you actually tailor yourself. But you still need a core set of tools that you can work with, which will make your life easier when working with time series. Out there are tools for time series, but most of them are for econometric time series. So basically, growth of GDP over the years. Big deal, right? You have 300 years of data. Okay, you have 300 data points. Wow. So that's not gonna scale for machine data. So you need tools that were engineered for machine data. Then you can do econometrics with it, but the other way around doesn't work. No questions? Okay, I have a few stickers here. Please grab one, put it on your laptop, or put it somewhere in the school.